and but still morning, Monday, during our consecutive lecture today. So we continue, we take over from the point we finished last week, which means that we are at various codes. So various methods of reading binary numbers, reading reading used in so various methods that are used in technique in various IT areas. Yeah, so we discussed about reading with respect to sign. And we started the BCD numbers, so binary coded decimal numbers. So the numbers which are a bit strange in this way, that instead of reading 10010 as 18, this number is actually read as 12, because we split the number. We split the number into two quadruplets, and we then decode those quadruplets normally, so according to the standard decoding method. Any questions? Because I still have, some of you still have microphones switched on, so if you have a question, of course, don't hesitate. Otherwise, please switch off. Okay, so then 18, for example, is not 10010, but 0001, and then 1 and 3 zeros. That's the BCD. That's the BCD coding. We mentioned about it that not only 8421 systems are theoretically available, because we can think about different systems. So also for BCD coding, the systems like 2421 and 5211 are theoretically available. Although, frankly, again, I mentioned about it, and I would repeat it, in BCD coding, from practical point of view, they do have a sense, and of course they are used in practice. But in majority of cases, in generally through my whole life, my whole professional career, only 8421 I was using, and I noticed anybody using. Although, of course, be aware that this is not the only possibility in case of BCD, so that there is a chance of using, maybe sometimes somewhere during some project you will notice also another coding, another BCD coding. But normal, the standard one, the one that you must know, is 8421. Mind that in this coding, in this BCD coding, the difference between BCD is that we have no A, B, C, D, E, G, E, D, D, and F like we have in the hexadecimal coding. In the alphabet, the options of 1 0 1 0 1 0 1 1 and 1 1 0 0 and so on. So all the codes which we code in, which we read as 10, 11, 12, and so on, in BCD they are not existing. So they are maybe not illegal, but actually they are not existing, because in BCD only the codes that you can see in this table are valid. So the codes from 0000 to 1001. The codes outside of this alphabet are not valid in the BCD. Code. Sometimes they are used in BCD coding for special symbols, but it really depends on the implementation. There is no universal way for coding or for doing this. Yeah, how to code from binary to BCD. So where the BCD is used actually, and does it have a sense of using it? Actually, the BCD normally during internal operations during internal arithmetics in microcontrollers or in programmable logic, because it's the same. Actually, there is no sense of using this BCD, because in the BCD, as you can see, it's less dense, because instead of so we are losing on the density of our notation, because instead of 5 bits like here, we have 8 bits. We have 8 bits, as you can see here. So for normal arithmetics, where the binary is good enough, then use binary. So don't even think about using BCD codes. The BCD coding has a sense only, in fact, when a human being is around. So when we need to make a HMI, so human machine interface, because we have 10 fingers normally. So yeah, we mentioned about this using 12. So using dozens last week, but here in case of BCDs, we are using it because of course we have 10 fingers, and people like to use decimal numbers normally. So this is actually for supporting the interface, and that's the major use case for the BCD coding, supporting the interface to a human being. So various things are used for this, but mainly it's about displays, various kinds of displays, where this BCD coding has some use. How to convert from binary to BCD? Again, it's a very simple algorithm that you can try to written in pseudocode. You can see it here, algorithmically, maybe not in pseudocode. So you have most significant decimal number, so MSD. Clear the result of MSD. Subtract 10 from this 8-bit number. If the result is negative, then you have to add back 10 to 8-bit number and return. Otherwise, you increase MSD and go back to this loop. So actually, it's an algorithm for division. And naturally, we can have an algorithm with division. So like before, for converting between binary and decimals. So this is the algorithm for microcontrollers, or for the cases where no division is available, or when the division is too expensive to be performed, and then we do the subtraction, or where we need actually where we know that the number is small. This is actually also the simplified algorithm for numbers from 0 to 99, as you can see, because there is no, and for 2-digit BCD numbers, but naturally the binary numbers, the BCD numbers, can be longer, so they can have any length. So it really depends on the number of quadruplets here. So we can have, of course, any number, and we can have the BCD, which is 40, which is 4 digits long or 6 digits long. Then naturally this algorithm must be modified. To include subtracting of 100, of 1,000, and of 10,000, for example, if the number is to have a long many digits. The BCD number, for example, that we want to convert. Anyway, this conversion is division-less conversion, and that's the advantage. But the problem is that unfortunately the number of the number of iterations here in this conversion, first of all, is not constant, because depending on the number, on the converted number, so it will be different for when converting, for example, 9, because then we finished here at once. So it's just about 3 operations that need to be done. But the worst is if we have 90 and 99, naturally, because at 99 the number of iteration would be about 9. So plenty of operations that need to be done in this algorithm. So of course today, in the microcontrollers that we are working with today, it's really worth first checking. Would it not be better to use simple division? Because with division it's just that we divide by the original bit binary by 10, and then we multiply it by 10. Because when we divide, we get rid of the remnant. And from it, the integer part, we multiply by 10, and we subtract the result. From. So, for example, maybe I'll try to draw this algorithm. So, first thing is we divide, let's say, this 99 by 10. As a result, because it's an integer division, we have a 9. The result. So the 9 is our MSD. But then we make an operation of 99 minus 10 times 9, which gives us this the LSD, which is in our case 9. So we have the MSD here, and we have the LSD here. So that's the second algorithm. It looks here. It looks much better than. It looks much better than this iterative algorithm, because we have no iterations. So the operation always takes the same amount of time, because we have just division, multiplication, and subtraction. But then this is the disadvantage of this method, that we always have division and multiplication. Subtraction takes negligible amount of time, but division and subtraction is a problem. So therefore, in case of microcontrollers, this kind of conversions, you always have to check what's the penalty, what's the price that needs to be paid for the division and for the multiplication, and then you have to decide which algorithm of the conversion should you use. Same thing is about the conversion in the second direction, so from BCD number to binary. So the simple iterative algorithm you can see here. So we subtract 1 from the MSD, because we have the number like this, let's say 98. So first we subtract 1 from 9, because we have this quadruplet. So we get 8. If the result is negative, then it means that the MSD was 0. Otherwise, we add 10 to 8-bit result to the final result. So we make the final result, it was 0, and we make it 10, and then we go back to step 1. So then we go with 7, then 20 here, and so on and so on. Of course, in case of the algorithm with multiplication and division, this time no multiplication is necessary. Therefore, this conversion, the BCD to binary, is simpler, because then it is enough for us naturally to take the MSD, multiply it by 10, and add the LSD, the 8, and then we have the binary 98. That's the case. Yeah, that's the conversion with non-iterative conversion. So here actually this is much more realistic, because it's faster. It's usually faster than the iterative algorithm. Although here it really depends on the microcontroller. So binary to BCD, here there is no rule, because it really depends on the penalty or the price or the complexity of the division at the used microcontroller. Here, usually even at weak microcontrollers, this conversion is it's simpler than the iterative version. Yeah, the nice stuff starts, and then nice. But the word would be nasty, because it's really unpleasant. About adding, you shall remember from previous week the addition of the simple binaries, which means that even with sign, so with U2 sign or with in unsigned version, this is actually the same. So you just add zeros and ones with a simple adder, because actually it's a chain of adders. We'll talk about the adders as logic structures within a few lectures. But in case of BCD, this gets way more complicated, because when we add, actually the problem is that we have the number like 17, and we have the number like 81, let's say. And then adding everything is fine, like here that we have 98. So we just add this quadruplet, because this is quadruplet and this quadruplet, and we don't get beyond the quadruplet. So the result of the LSD addition, for example, doesn't go beyond 9. But if it goes beyond 9, then we have to play with carry. And this is done actually in this algorithm where we need to add 6. So there is the addition of 6. This is automatic algorithm. Automatic, of course. It doesn't sound so, but it is actually the algorithm of adding 6. 6 means that we carry the result from one quadruplet to the other. So Frankly, it's in my opinion today microcontrollers would be faster and not to avoid this arithmetic. Therefore, yeah, you can analyze it at home, of course, this algorithm, and you can try to implement it. Algorithm like an algorithm, so it's not very complex. So we don't have time here to read it actually, but you can try to read it, to exercise a bit and to read it or to implement it. For example, in C just to exercise your skills or to improve your skills about writing various codes. So this is a good algorithm for this, but actually, in my opinion, is the only good thing about this algorithm. Because today, if you are using BCD numbers, usually you're using them only at the interface side, so only when the HMI interface is involved, or when there is some human being and needs to have a decimals. In all the other cases, so internally using BCD numbers, we say, what's the sense? Actually, it's not much, because normally for binary numbers we just need this operation, and for BCD numbers we need all the rest of the stuff. No sense, frankly, no sense. So again, this algorithm, yeah, even I put here this subtraction. So if you want, you can practice on it. But yeah, if you have nothing more interesting to do, and if you want to practice some programming, some algorithmic programming or implementation of some algorithms, these are very good algorithms. So you can screenshot those and try to implement at home in any compiler that you want, with any programming language that you want. But from practical point of view, this subtraction and addition, so arithmetic operations on BCD numbers, have really very, very little sense. Okay, let's go further. Next method of reading the same. Next method of reading zeros and ones is the method of reading them as fractionals, as fractional numbers. Thus far, we've been analyzing only the reading when the bits have an integer weight. But this gives us naturally the integer numbers. The integer numbers are very nice, are very useful, but you know, the world is not only about integers, and very often we need to have some fractions, some fractionals, and there, of course, there exist two methods of coding the fractionals numbers in the binary numbers. The method number one, the simpler one, is this one that we'll talk about, or we analyze it now. This is the fixed point number, the fixed point method. While the second one is a floating point. It's about the floating point coded, which is more universal yet more difficult to be performed. About the floating point we'll talk a bit later. Of course, we analyze it as well, this method of coding, but within a few lectures it is, if I'm not mistaken, 2, maybe 3. Anyway, the fractional numbers, the idea about the fractional numbers is that we change the weight of the position of our normal binary number. So instead of the LSB having the weight of 2 to the power of 0, which is the weight of 1, we decide to assign a weight to the LSB, because this is naturally the LSB position. This is an example of 16-bit number. We assign the position of the bit to be 2 to minus something. Yeah, these are so-called fixed point numbers, fixed point fractions or fixed point numbers. Fixed point means that we have 0 at a fixed position, but 0 at a fixed position, so not 0 but 1 at fixed position, the weight of 1 at fixed position. But fixed position here doesn't mean that it's always and everywhere. The fixed position really depends on our personal application, because for during one application the fixed position may be at position 6, like it is here. The weight of 1 may be at position 6, because it's counted from 0, 1, 2, 3, 4, 5, 6. But in other applications, this position, the position of 1 may be here, for example. In other applications, maybe here. In other, maybe here. That's quite natural that we change, that we adapted the fractions to the fractions notations to our need. On the other side, that's in my opinion a very strong disadvantage of fractionals, of this method of coding fractional numbers, because they are not universal, and if you don't keep within your design, if you don't keep the decimal point at the same position, at the same bit, then even in your design you may get false results. And of course, if you start to share the code, or if you start to compose your software with codes from developed by other persons, each one can use different fixed point position, meaning that you may have really false results very easily. So that's the disadvantage of this number, of this method of coding. Yet it has pretty decent advantages. The major advantage of the fractional method is that we are using actually a very similar arithmetic to the integer arithmetics that we spoke, and that we'll be analyzing in a bit further for multiplying and division, for example. So the same arithmetics and the same calculation units, various logic or arithmetic units can be used when dealing with fractions, because fractions are behaving similarly. It's just about how we read it and how we decode it, the binary. Here you have the example of this binary read as a fractional. So this is the binary of hexadecimal is 9A, because it's this red hexadecimal is 9A. Of course, we can read it with a sign. We can read it as the we can't read it as BCD, by the way, because it's 10, so this symbol is forbidden. But we can read it with sign. We can read it without a sign. We can read it decimally as a negative number. We can read it as positive number decimally as well. It's 128 plus 16 plus 8 plus 2. So it's 138, 148, 154 decimal in this number. But if we decide on having a decimal point here, then we can decode it as according to this table, more or less, because this table is for 16-bit number. But if we put a decimal point here, that the weight of this one of left bit from the decimal point is 1, then the weight of this one is 2, 4, and of course 8. While the weight of this bit is a half, this bit is a quarter, this bit is 1/8. Sorry about it, but I'm not really sure why the PowerPoint is doing like this. Been trying to change it, but I failed thus far. And this is 1/16, and this is 1/16, the weight of this bit. Which means that we can compose such a number, such a nice fractional number can be composed of only zeros and ones, so no special coding is necessary. And then we get to the major advantage of the fractionals written in this way, is that we can use integer arithmetics, and we can use integer microprocessor cores for working for operations with the binary, with this fractional binaries. because actually they are like normal binaries. It's about decoding them or reading them. Decoding, it's about reading them, and only depending how we read them, then we get different number. But the operations from the microprocessor's point of view are the same, which is very good because we don't lose. There is no need for special hardware or for special processing. Actually, this is very similar to normal binary. You will have a comparison when we talk about a floating point coding. You will see by yourself how much more difficult and how much more complicated the operations on floating points are. Yet, of course, the floating points have certain advantages compared to the fractionals. But we'll talk about the fractionals, about those advantages and disadvantages of floating points against fractionals when the time comes. Then an example of conversion, some floating point, some fractional number, decimal number to a binary version. So we do it. The algorithm is again iterative, and the algorithm is that we multiply our number by 2 all the time, and when we observe 1, as the integer part, then we take this one as the MSB of our number, and we subtract then this one for further processing. So we actually take the 1 here and we leave 0, and then we multiply. So we leave 0.09375, like here. We multiply it by 2, and then we get the results, and then again we check if this is 1 here. Now it's 0, so we put 0 here. Then we get 0 again. We multiply it by 2. We get 0. We multiply it by 2, and then we get 1. So we take 1 as the bit number 4 of the fractional part, and we subtract it again. Then we multiply it by 2 again, and we get to 0, which means that this number rounded down. So there is no error in conversion between the decimal notation and the binary notation of the fractional number, of the fractional part. Of course, it might happen that we are not able to make a fractional notation without an error, without a remnant of a decimal fractional. That's one of the examples. Of course, there is an infinite number of examples, an infinite group of numbers that are converted this way. So they are converted with some error. So take a look at 7, for example, this 743. We multiplied by 2. We get 1 here, so we take the 1 as our MSB. We have a remnant. Then we go proceed with this looping. We multiply by 2, and then we land at this point where we have 408, and then we have 416. And then when we multiply it, we have 832, 0.832, and then 1, so it will be 0, then additional 1, and so on. There will be some period here about the zeros and ones, but actually it would mean that we can only get closer to this value, to this 743, but we will not get actually exactly. We will not be able to reduce the error to 0. There will be always some remnant, which means that we need to stop the iteration at some point. Of course, we stop the iteration at the size of our number, the size that we want to use. Practically, we use fractionals, so there is little sense, again, going back to practice, there is little sense of using there is little sense of using fractionals when we are dealing with 8-bit arithmetics. So in 8-bit microcontrollers, the 8-bit fractionals, they allow us to, like here, we have a precision of 1/16, which means that we have a precision, not the greatest, but still some fractional precision we have. But with 8-bit number, the integer part can be only 15 here with the decimal point in the middle. So plus minus 7 or minus 8 plus 7, and the fractional 18. 116, which isn't too high precision. In case of using 16-bit numbers, then the fractionals have much more sounds. Here, the decimal point is not in the middle, therefore we have 1/32 as the fraction, as the resolution here of our number. Which is so-so resolution, but still we can move the decimal point, for example, to position up, and then we will have 256, for example, as the resolution, which is in many cases quite decent. Although frankly, in case of fractionals, when I'm using it in my designs, I'm using the fractionals in 32-bit precision, to be exact. It's as a simplified version of a floating points, because floating points mainly we are using at 32-bit long. They are 32-bit long, so when I'm not having any floating point unit available in a microcontroller, then I'm turning to fractionals, but then I'm using 32-bit fractionals, because the 32-bit fractionals, their decimal point can be placed, for example, when placed in the middle, allows to code the numbers from 0 to 65K with the resolution of 1/65K, with such a resolution, which is really decent, and which allows, from the technical side, to code very many nice things like high resolution temperature readout, temperature sensor readout, or pressure sensor readout, or this kind of thing. So the 16-bit fractionals have a sense, but 32-bit much more. 8-bit not really. So rather than try to go into this direction in your practice. Okay, next method of coding. This is a strange code we call gray code. This is, as far as I know, not the same gray which was in the film. Anyway, he's Frank. I don't remember the name of the gray from the Gray movie. Anyway, the guy here was, I think, much older. He introduced the code, which is named after him, the special feature of this code, of this gray code, is that it differs, the positions differ only in 1 bit. There's 2 successive positions, 2 successive values, and it sounds strange. Because here is the table. So it sounds strange because it looks actually as well a bit strange, because instead of simply 0001, 0010, 11, and so on, we have things like 01, then 11, then 10. Then goes even stranger, because we have 110, then we have 111, then we have 101, then we have 100, and then we have 110. What a surprise! Completely different mind that we are accustomed at the binary code. But the idea about the gray code you can see here, and that's why it was introduced physically. It was introduced physically on the market, is to use it in various encoders or various devices. So it's even written here, I think. Electromechanical switches, for example, because we are reducing the frequency of changes. We are actually reducing the frequency of changes, because mind that this is the coding when we have some switch or some encoder, and the positions are coded with 5-bit binary, and here is with 5-bit gray code. Here, the frequency of changes of those positions, and this one, and even this one, the frequency of changes on the binary code is twice the frequency of changes of the gray code, which does mean that with the simple change of coding, we are gaining on the RPM, possible maximum RPM of this switch or encoder or whatever we are having. It's a great game, mind that. It's a great game because actually it's about just reading back. So instead of reading this way, we are reading this way. That's simple. So we just need to slightly different logic, but actually that's not a problem. But we are gaining a lot in case of frequency readout, in case of frequency characteristics or required parameters of the electronic path. So that's the reason, that's the major reason why the gray code is used extensively in various encoders, extensively. So it's used everywhere there, because of this reason. Additionally, it's very good for code correction and error checking, because we have again two neighboring positions are different just on one position. So it's very easy if we are expecting, for example, that some device is delivering its states, and we know that the states must differ only by one position because they are to be successive states, which means that they must differ by just one position. So additionally, we have the gray code, besides the reduction of the frequency, required detector frequency. Additionally, it gives us the chance to check the errors and check the transmission errors of various EMI noises problems, because then we have a control, direct control of what shall be available and what we get on our inputs. So these are two elements why the gray code is used, and while the BCD numbers are used from time to time, actually, thus the gray code is used extensively. So we are using binary code and we are using gray code, of course, in different applications, because gray code binaries internally in microcontrollers. The gray code is usually used as the output from various electromechanical devices, but the microcontrollers very often need to be able to understand the gray input, and very often they have specialized blocks for understanding the gray code. We'll talk about the logic, and we'll talk about what the gate means in the short term, because it's the plan for today, or maybe early next week. Early morning next week. But in general, the decoding between the gray code and binary is very simple. So it does require just 3 XOR gates, and that's it. Which means that although it does look very complex to decode it, and yeah, you might wonder that a very complex algorithm for doing this. Then on microcontrollers, we are decoding it with lookup tables. That's simple. While electrically, we are decoding just with 3 gates. So mind that we can save a lot of energy, we can save a lot of problems in electronics, thanks to this coding, because we are reducing the required frequency or the output frequency from the sensor. Yet we still can interface very easily such an encoder, such a gray encoded element or gray encoded sensor to a simple binary microcontroller, because it's just really enough to use 3 simple XOR gates, so exclusive OR gates. So depending if we want to convert from gray to binary, then we are doing it this way with this combination, and in the other way we are doing it in this combination. We'll get back to this schematics when we will try to implement some logic and use some logic equations. Then we will focus more on this, and we will try to design it. So you will see the truth table and the transition from truth table. I will show you from truth table to this very nice logic circuits, but that will happen when the time comes. Now it's time for another encoding. This time ASCII character encoding. ASCII character encoding. So this time So what is ASCII? ASCII stands for American Standard Code for Information Interchange. As you can see, interchange, which means that it's for communication between two devices. This is the character encoding standard developed several decades ago. This standard of understanding what the binary 7-bit first, then the 80-bit 8-bit number means, how it is, what's the meaning of this combination of 7 or 8 bits. It was and it's still in use, so it has been in use for really many decades. Only during recent decade or two, maybe 1.5, the ASCII encoding starts to be replaced by Unicode. So instead of that's actually similar thing, but in case of Unicode, you know, the first problem with ASCII is that ASCII is mainly for alphabetic characters, but it was American, which means that the ASCII original was just for English alphabet. Plus numeric digits and punctuation marks. Then, of course, the Europe came in, and for example, Germany or Poland with special characters. But then the rest of the world came in, especially China, Japan, with their very, very special characters and a very huge market. So today the ASCII is not enough. So that's why we're using Unicode. Still the major in case of microcontrollers. While on large computers we are using 16-bit and 32-bit Unicode, because the 16-bit Unicode is good enough for Chinese marks, but the 16-bit is not good enough for all those smileys. And actually, especially for the smileys, we have the 32-bit Unicode right now. But anyway, in microcontrollers, we are using smileys not that often. Therefore, in microcontrollers, the ASCII coding still dominates, especially when we want to play with text. It really does dominate as well within the TCP/IP, for example, communication. So many parts of engineering, the ASCII coding is still not replaced. It's still not replaced. So it is the process of replacing goes on. So in large computers, it's very advanced, but in microcontrollers, this standard is still a standard and it's still used widely around the world. So it's still widely used. So some important things about the coding is that we have, so everything actually is in the table. So there is the ASCII table where our decimal or hexadecimal or binary number means something. So that's about the ASCII. So this time, for example, 1001, the number that we had before, so 9A, does not mean 9A, but it means some special character, because the ASCII table is split into two halves. The first half, so from 0 to 7F, so the 7-bit half is universal, while the second part of the table is being changed depending on which characters are to be coded. Therefore, the second part of the table is replaced, and it's not universal. So it really is a coding table. It is called a coding table, and depending on the need, we can use different coding table for Middle Europe, for America, from Asia, and so on. So we have different coding tables, which are the second part. The first part is universal, and it's very critical. It's very important from the microcontroller's point of view. And again, we'll get back to this after the break, to the analysis of this table, ASCII table, after the break. So let's have now a 15 minutes break, and we'll get back to this after a short break. So let's analyze the ASCII table because it's a bit regular, and it's really, in case of microcontrollers, very worth knowing what's there. So what's the coding? So we can split the table into a few areas. Area number one, this is the area actually from 00 to 31 decimally. It's 1F. These are the control symbols, various control symbols, like like null. 0 is null. What a surprise. Like start of text, maybe not so important, but end of text, end of transfer, and backspace. Yes, backspace. What is very commonly used is the A line feed and form feed. So 0A and carriage return, especially. So 0A, A, C, and D symbol hexadecimal values are decoded as those three operations. Very important one, and then all the others more or less interesting from our perspective. But actually, from my perspective, those four symbols are maybe backspace as well is used from time to time. Then we have the second part. In the second part of the table, we've got various symbols. So those symbols are available from 20 to F hexadecimally, or from 32 to 47 decimally. So these are various symbols like space, like exclamation mark, and so on and so on. So you can see the symbols here. And then the second part of the symbol starts from 3A and finishes at 40. So this is the second part of the symbols. And the third part of the symbols, what a surprise, third part, not the last one, is from 5B to 60, and the last part of those symbols is from 7B to 7F. So four sub areas dealing with the same. So when the various symbols that you can find on the keyboard and you can find in the text, in various texts where they are coded. So this is part 2. All those split into, as you can see, four subparts. So subpart 1, subpart 2, subpart 3, and sub area 4. And then we have the third area, or the third block. The third block is the block of numbers. Numbers are coded from 30 hex to 39, so 48 decimally to 57 decimally. This is area 3. Then area 4 is the area with capital letters. So they are coded with different numbers, different values than the lower letters. So capital letters starting from 41 hexadecimal, lower letters starting from 61 hexadecimally, no special marks. So this is English, pure English alphabet, which is from A to Z, capital and lower. If you want Polish letters or some other Spanish or German or Chinese letters, then they are available in the second part of the ASCII table. But if you want to know more about it, turn to references. This is so we don't need them here. We don't need them at this moment to analyze those tables. So as you can see, the table is quite regular. And we are using it extensively within microcontrollers for various purposes, but mainly, of course, for coding signs, coding characters, coding text. Quite often we jump from binary to characters. So coding from binary to characters means adding 30, because that's the difference. So 0 binary is 30 in ASCII table, so 1 is 31, so on. So it's enough to add 30, and from binary you have a character, which is stands, which marks 0. Same is in the reverse version, in the reverse way. So when you have a character, you can subtract 30 hexadecimally or 48 decimally, and you get back to a binary value of 0, 1, or whatever you want. So that's the ASCII table. Very important thing in engineering, in practical applications. If we talk about the understanding of binaries, of understanding of the numbers, we must not omit also one more small thing connected with the security of the data transfer, especially, and with the security of binary numbers within processing systems. These are so-called codes for error correction and error detection. Yeah, when I was a student, I remember having the whole semester lecture only about the codes. So this is a very wide subject. That these are the codes. It's mind at the codes. So I want to do it with you within 15 minutes. So of course it will be much more limited and no theory. Again, if you want to get into theory, let me know. We can make such a lecture. This correction and detection codes are don't mess it up with the security coding. So with all those hashing or with hashing algorithms or with various AES techniques, for example. That's not it. That's not for this purpose. It's not as complex. That's not about for cybersecurity as such. It's only about the data transfer, so it's much closer to hardware that I want to show you. Although it's very practical, those codes, as you will see in a moment, are very practical, and they usually used for very often. They're used during the data transfer, during the various interface within various interfaces, communication interfaces in microprocessor systems. That's why a few slides about it. So the main problem, and that's why we are using those error correction and detection codes. Again, they are not for security. It's another subject. So if we have enough time during engineering course, during advanced applied electronics, there is a special lecture about it. But not now. Anyway, the error correction detection codes are used to take care of the noises which in the communication channel which may cause the errors in the transmission. So which means that we are transmitting something and we are receiving something different with some errors. Depending on the channel, the chance of the error is greater or lower. We estimate it with a special measure. This is a bit error rate, so Baer measure, which tells us about bit error rate, which tells us about mind that the B is written here in capital letter. So another inconsistency, because it's like a byte error rate, but it's a bit error rate. So plenty of inconsistencies here. But putting it aside, the bit error rate tells us how many bits what's the chance of having false bit, of receiving a false bit in the bit stream. So the bit error rate is given into this measure is given as a fraction. So it may be like 10 to minus 6, for example. 10 to minus 6 bit error rate means that one bit, there is a chance that one bit, so statistically, 1 bit per 1 millionth of bit transmitted is false. Has an error. And yeah, it happens depending on the channel. We may count in very good optical channels. We may count with Baer's 10 to minus 9. While in the radio paths, there it happens that the Baer is 10 to minus 2 or 10 to minus 1, even although 10 to minus 1, that's actually something you can see here on the slide, because it's about 10 to minus 1, because the number of bits transmitted is 2, 4, 6, 8, 10, 12, 14, 16, 17, and 3 errors in 17 bits, so it's 10 to minus 1 about Baer here. It's quite seldom, because it means that the channel is very, very lousy. But still, even if you have a Baer of 10 to minus 6, you still shall be able to detect the errors and shall be able to protect your channel, protect your information against the bugs and against the errors. And that's the reason why we are using error correction and or error detection codes in technique and in various communication channels. So the basic rule is actually to because we have two things here. So there is a lot of theory about it. So again, to make it simple, the correction and detection codes, they both share the idea that there are two common things here. The common thing is that we have to add some extra bits of that are transferred. Those extra bits, in various ways, they are used to detect and or correct the code, because first we start with detection. The detection starts first, correction goes second. So when first we need to be able to detect the codes, and then we are able to correct. That only then we can be. It may be possible to correct the problems, to correct the errors. And again, the common thing is then the more additional information is being sent, or the more additional bits are being sent, the easier is to detect problems, or the more problems we can detect, and then starts a possibility to correct the problem. Depending on the algorithms, depending on the methods, there are different possibilities available, or different number of additional bits are giving us different possibility of correcting one bit of error within our frame, or 2 bits or 3 bits, and so on. And same is with detection. Again, we don't have time, and there is no space. Again, there is no sense during this lecture particular to get deep into theory. And there are a couple of methods of doing that detection and correction. So again, this is a pretty large technique area of technology. We have block codes, and we have convolutional codes. That's first classifications, where we are adding this additional information, correction slash detection slash correction information, either as a block, as a unified block of zeros and ones, or we are adding them as a convolution in the convolution version, when they are intervened between the normal bits of information. Both ways have some pros and cons, depending on our needs and on our particular application. Either of those can be used. It's again out of the scope of this lecture to analyze it, to analyze these details. For example, like especially the convolutional codes are very complex. Very common today are Viterbi coding and turbo codes, so they are very commonly used because they are giving the best results, especially in a noisy radio channel, because the radio channel is not very trustworthy, and the data transfer there is problematic because of all the problems we have in the radio path. And the radio, everybody wants to use radio today. Therefore, this convolutional coding is really in use. But again, they are a bit too complex, especially for this lecture. But for today, I would like to show you the simplest versions. The simpler versions are good enough they are not good enough for radio transfer, for radio layers, but for the normal communication, they are more than good, more than enough. So these are 3 methods of block coding. So during normal microcontrollers operation, even at higher levels. So for example, when we are transferring TCP/IP frames, if they are transmitted over, for example, 5G or 4G, then at the radio layer, those kind of complex convolutional coding is used to get the most out of the bandwidth. While on the IP and TCP and UDP layer, everybody is using today either of those coding, so the block codes. Therefore, we'll not talk about those convolutional coding, but a few words about this simple block coding. So the parity checking, checksum, and the CRC. First thing, the parity checking is the coding which was very popular and still is very popular with ASCII numbers. So the ASCII format, as you shall remember, original was 7-bit, and to this 7 bits of data, there was added 1 bit of parity. Parity means that we are adding additional information. Again, this is this kind of coding. So additional information, this time 1 bit of information per 7 bits of data. And this bit of information, this correction of parity, is set to 0 or 1, depending if the number of zeros is positive, or if the numbers is even, or if the numbers of 1 is even in the original number. So this is the original data. So this means that we have even and odd parity, meaning so it's even depending on the number of ones and of zeros, we have either 1 or 0, as you can see here on the example. So if there is 0, if there are no zeros, no ones, so it's an even. In the even parity we get 0 as the parity bit. In the odd parity we get 1 as the parity. If there is 3, if there are 3 ones, for example, in the number, it doesn't. Then there we have 1 as even and 0 if the parity is chosen as odd, because we have two systems, even and odd. It means that we have two systems. The systems are marked sometimes 7 and 1 and 7p1. So these are the systems. So the n and p means which parity it is, and here we have the initial information length, and here is the number of bits of parity. Theoretically, we can have more than 1 bit of parity if the number is longer, but usually we are using just 1 bit parity in practice. Of course, it's no change here if the ones are spread as here, or if the number is like 0 0 1 1 1 and then 0 0, because it's also 3 ones. It will also get in the even parity here as 1. In the odd, here will be 0 in the most significant bit, or in the parity position. This code, so this parity checking gives us makes it possible to detect. It's only detection coding, no correction possible here, but it's for it will detect 1 bit of error or odd number of errors in the number, because if we have an even number of errors, so if, for example, 0 is changed to 1 and 1 is changed to 0, so 1 is changed to 0 and 0 is changed to 1, then we are not able to detect it. But if three bits are false, then we will have an information that something is wrong. So all even or odd numbers of errors it is possible to detect odd number of errors with the parity checking. So this is a very simple really very simple mechanism that is used in some especially in UART, because it's originally UART based, but it is used from time to time. I'd say this way. It is used from time to time. It's not maybe the most common today, because it's the major disadvantage of this parity is that it is byte based. Usually it is byte based because it's for 7 bits of data. Sometimes it's used for 8 bits of data when we have the system 8 and 1, for example. So 8 bits of input data and 1 bit of parity. This gives us 9 bits of output. And from practical point of view, this is not very very good. In fact, that's why very convenient. Maybe this word is better. Very convenient to use. Therefore, the parity checker, although it used to be very standard, today, because it's byte based and because we are very often transmitting more information than just 1 byte, then the parity checking it's not as commonly used as it used to be. It is in use, but it's not as common. The example, how much does it give us? Was the detection capability in numbers? Theoretically, you can see here. So if the single bit error probability is 10 to minus 6, then the probability of the error of the 8-bit 8-bit channel is of a parity checked version is at 8 times 10 to minus 6, and if but the possibility of the double error is much lower. That's why the parity checker has a sense, because it's able to detect this error. A double error is rather unlikely then. So 10 to minus 11 is very low. So this parity checker is then very good enough, because it delivers us the information very easily about the single error problem. Second mechanism of checking, of detecting the errors, because it's another mechanism that is not helpful in fixing the problems and fixing the errors, but it's a mechanism for checking it, is that we are calculating a checksum, calculating a checksum, which is usually a sum of some sort from a block of data. And this is the checksums are actually very similar to parity. It's the extension of the parity, but we are, instead of working on bytes only, we are working on some blocks. And this is really an advantage, a small but a game-changing feature of the checksum. Which because it's we can use it on any block size. We can decide what will be the size of the checksum. So instead of so we are actually adding we are actually, in case of checksum, we are adding, so I don't have a slide here, how we are doing a checksum calculation. We are doing it actually this way, that we have a block of bytes. That's how we do it. We have a block of bytes, let's say 3 bytes, because we can have any number. That's very nice about the checksum. And the simple thing is that we are just adding those bytes together. So we are adding those bytes together, and the results we place here in the additional byte, because again, this is a block code. So that this block of auxiliary data, of checksum data, of error detection data is placed in the last in one place. So it's placed in this additional byte. So instead of 3 bytes initial, we have 4 bytes, 4 bytes of data. Yeah, we can have then what we are doing during the reception, when we receive the data, because this is during the transmission. What we are doing during the reception, of course, we are receiving 4 bytes of data, because the frame is composed of, in our example, of 4 bytes of data. And with the checksum, we are just adding those 4 bytes together. We are adding those 4 bytes together, and we are comparing if the final result is 0. So actually we are XORing this last byte, because it should be the same. So we are adding normally this 3 bytes and XORing the 4th byte with 4 bytes, and we shall receive 0. If we receive 0, then during the reception, if we receive 0, it does mean that the message is unaltered. If it is non-zero, it means that the message is altered, and there is a bug inside the message, and the message has to be rejected. So the parity check, the checksum is simpler from the microcontroller's point of view. That's why it is used in the parity checking. Why? Because mind the simplicity of operations here. In case of checksum, we are doing it as simple as this one. So we are just simply adding the bytes, byte by byte, or word by word, because it really depends how much additional information you want to add to your data frame. So we're using simple binary operations to generate the checksum, and then simplicity of checking is again very easy to check and very fast, because we are just making simple arithmetic operations of adding and XORing. This is a very basic operation as well. We are adding and XORing the data, or making a comparison, because we can also compare the sum here with the value of the checksum field. And they must be the same. If they are the same, then the information is unaltered. This is much easier to do than in case of parity checking, because with parity checking we have to compare the number of ones in the message. From practical point of view, it's more time consuming to do it, to make the comparison, because yeah, you can see here that it does seem simple, this comparison, because yeah, you just take a look and see, okay, there are 3 ones, there are 4 ones and 7 ones, but remember that from microcontrollers point of view, we have to bit by bit analyze the input data and check out how many and count those bits. So we have to check each data bit in fact of information. So for the frames consisting of, let's say, I know 100 bits to 100 bits of information, we have to check count every bit in this information, which would take a huge amount of time, because a couple of hundreds of cycles. And here with the checksum, it's about a couple of additions. Simple operations, usually single cycle on a microcontroller, no looping even here, although maybe a looping, of course, because we can then increase the number of input bytes or input words of information, and then simple code as the final. The decoding is as well simple. So the checksum from the microcontroller's point of view, from the application's point of view, again, from my perspective, from point of view, because from my experience, the checksum proved to be very, very valuable mechanism. It's not as good as the next one, so it's not as good as the CRC, frankly, but still it's very simple. And for small microcontrollers, the checksum is definitely better than the parity. That's also the reason why the parity is used also today quite seldom, only in some hardware accelerated parity checkers, like the UART blocks in microcontrollers. They have the hardware parity, then we can use the parity. But when we don't have the hardware parity accelerator, which is usually the case, then calculating parity manually have no sense today, and the checksums are used instead. The special version of the checksums that we are using are the CRCs. So they are cyclic redundancy checksums. They became a standard actually in wire data transfer. So basically all algorithms that are in use today for wire data transfer, and some also for wireless, although wireless are usually using the better ones, are using the complex convolutional coding. But for simpler wireless and for all wired transfer, the CRC checksum, so these versions, cyclic redundancy, are in use. What's the difference here? Because the idea is fairly same, that we have a block of data and a block of the remnant of the code, but this time the block of remnant is generated by the special by dividing our data by a special divisor. So we are making a binary division, but formally it's mathematically a division by a polynomial. So we divide it by a polynomial, and the remainder of our division is then added as the CRC bits. And then in the receiver, so in the transmitter, in the sender, it is done this way. Then if data goes through the channel, and in the receiver, we are dividing everything again through the same polynomial, and the remainder must be zero, non-zero. The remainder is rejected. So actually, the idea is the same like with the simple checksum. It's just that instead of just simple adding of data, we have to make a division. So from this point already, you should see the disadvantage of this method. So the major comparing to the checksum is that we have to make a division through a polynomial. It sounds mysterious, and I will show you. I will clarify this in a moment. That's the disadvantage. So we have to make a division by a polynomial, not even by a number, but by a polynomial. While here in the first method that I showed you in the simple checksum, we are just adding bytes or words of information to each other. So this is the difference. So this is the difference between those two methods. Although although the CRC gives us much better response, so the protection of the data is much stronger here, and therefore the CRC became a standard. The simple checksums, like I showed you, they are used for, let's say, amateur data, data transfer, while the CRCs are used in all the other cases. So for semi-amateur and, let's say, professional, whatever it is. So how it works physically, so theoretically how it works, we have the message or the input data, which are the k bits of information, and then we have a code which is, so yeah, then we append the bits to the message of data. So k bits as the message, the appended bits and bits of this CRC code, and all this forms as the message. All this forms as a message which we can mathematically write as the polynomial. And what we are actually doing is that we are dividing our this is simply adding the mathematical, the visualization of this of this notation, that the binary number of binary message, how does it look in case of polynomial. So then we transfer this 10 10 10 to the polynomial. The remnant also we transfer to the polynomial. But how do we generate the polynomial? How do we generate this remnant? Actually, that's interesting. So we are formally dividing our message. We are dividing by the generator polynomial. So we are dividing, or by this one of polynomial. Division is done in the special logic structure. So there are this is actually this is actually a register where our information is inserted, is loaded in parallel, and then this structure implements actually this polynomial. So x to 4, x and 1. Depending on the polynomial, there is different number of XOR gates actually, and different number of registers. This is a simple polynomial for 4-bit of information. And then formally in this structure, our 4-bit of information is divided by so it is just clocked. After 16 clock cycles, what is left is our remnant of the division. This is formally, so this is 4-bit of information as the input, and the output is 4-bit also, and this is our CRC, or our checksum, and this value is added then to the initial information, forming the 8 to 4 CRC. We can have different polynomials. For example, with this polynomial x to 3, x and 1, so 1 0 1 1, we have the input of 0 0 0 divided by this polynomial gives a remnant of 0 0 0, 0 0 0 1 gives a remnant of 0 1 1, and so on. So this is, as you can see, additional information added to our initial message, to our initial data, and then the receiver expects when the data, when the information is 0 1 1 0, then the remnant, the checksum, is 0 0 1. The problem with CRC is from the beginning here, that it's very nice with the it's very simple logical construction, the CRC generators. The problem is implementation in microcontrollers. So in microcontrollers, we are either using these code tables, because you can calculate for each polynomial offline, you can calculate the code words, this checksums. You can calculate, and then you can simply simplify, make a lookup table where the data word is the input and the code word is the output, like you can see here on the slide. or we are using a C implementation. There are simple procedures for this, simply written, but quite complex, time consuming. Simply a simple idea, but quite consuming because we have to do some bit shifting here, which takes time on microcontrollers, and besides we must have a loop. Also, therefore, in microcontrollers today, because this technique is very popular, the CRC, therefore today microcontrollers, very often we can find hardware accelerators of CRC calculation, which means that there's these logic structures, those one, they are already implemented, and they are implemented in hardware. Therefore, we don't need to laboriously make a C coding and do it. And so, again, small practical remark: if you want to use CRCs and not simple checksums, but the CRCs, and search for a microcontroller with hardware CRC block inside, because that's actually what we are what's today available and what's today possible. Avoid doing it in program way. If you don't have a microcontroller with CRC hardware CRC checker, then prepare code word table. Again, avoids algorithm. The algorithm here, it's not very complex. If you want, I can share with you a code for it, but from my perspective, it's very time consuming. The good thing about the CRC is that we don't have to, because there is a large number of possibilities here with the polynomial, but we can use the ready polynomials already tested and already proved in many applications. So like CRC4, which is, for example, in the G704 as applications for ATM, for example, layer, we have CRC8, CRC10. In Bluetooth, so I mentioned about the wireless communications Bluetooth is using, for example, these polynomials, which you can easily use for your own purposes when transferring 16 bits. If you want a 16-bit block, additional block added to your information, or if you have more space to share, more space to be spent on the detection capabilities of your data transfer, then you can use the CRC32. So, and you don't need to really test your own and check your own CRC codes. Again, this is something that must be checked, because not all possible polynomials have the same detection strength. So it's really advisable to use either this or this CRC coding for the CRC generation in your applications. Took us a bit longer than expected. Planned the logic case for today. Fortunately, we'll just start it and finish it next week. So because we moved from the simple from the binary numbers and various coding of the binary numbers to the logic gates. First about I think I've already mentioned it, that the complete logic, and we'll try to prove it, that we can write any digital circuitry using just 3 gates. Those gates are, and the basic gates, I think you should be aware of those gates. It's not very difficult. I would say even it's very simple. Those 3 basic gates are NOT, and OR. The NOT gate, so the logic one, negates us the input, which means that the output. So this is a simple logic equation. So the output Y is negated A. It's mind the notation. So there is a line above the A. If we are not able to, because graphically we are not able to make this line, that we are making a slash. Slash A is same like negated A. The truth table, because this is again this is logic equation, this one, and this is a truth table. In case of truth table, we have inputs on the left, outputs on the right. On the right of the line, so input A generates the output 1, and 1 as input generates the one as output. We can have a buffer, a simple version of NOT, the version that logically does nothing, but the buffer physically is used for translating impedances, because that's the reason why we are using buffers. We are translating impedances actually. So it means that we have high impedance here and we have low impedance here. That's why the buffer is used. In other words, it's strengthening the signal, or it's isolating as well two parts of the circuitry. That's why we're sometimes using buffers even in logic circuitry. Although the buffers in logic is quite often they're used to translate the signals, signal levels, but about it slightly later. The second gate from the basic set. So the AND gate, this is the symbol. This is the logic equation of the AND gate. So just A times B, but no marking. Sometimes we're using just a dot here. Sometimes just a dot, but very rarely this dot is used. It's missed even. The truth table, so it's 1 as the output only when 2 inputs are high. So any inputs are logic. If any of the inputs is logic low, then the final result is low. Then we have an OR gate. The OR gate, it's different symbol. Here it's round, but in also we are using here some sharp ending. Yeah, this kind of, I don't know if it is visible, but sometimes it's not rounded here at this place. Sometimes it is sharp, and here we don't have a line but an arc. The output is A plus B, so we have a symbol of plus this time, but the plus is different than in standard arithmetics, because 1 plus 1 is not 1 0, but 1 plus 1 is 1. This is the OR gate with the symbol. Also, we have a couple of other gates which we are using in the logic circuitry. So we have the XOR gate with plus in the circle. This gate is actually much more similar to the standard arithmetic addition, because 0 plus 0 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 1 XOR 1 is 0, because that's what we would expect. So the XOR gate actually is more similar to addition than OR. Then we have a NAND gate, which is simply a negated AND, because it's XOR is a combination of AND, OR, and NOT, while NAND is a combination of simple AND and NOT. Same is with NOR, which is a combination of OR and NOT, so that's why it's A plus B negated. This is A times B negated, and as well the functionality. And of course XNOR, it's a negation of XOR, which is the A plus B negated. Okay, we are off time already, so it's already a break. So that would be it for today. We'll continue with the gates and the logic equations and all the theorems, logic theorems, already next week. So unfortunately I failed to deliver it today. It will take time. We'll analyze it next week. So thank you for today. Hope that you will join us next week. Goodbye. Have a nice day.
Goodbye. Thank you.